Okay, thank you very much. So welcome back to the auditorium, despite the very nice buffet and also an exciting volleyball game some of you are playing. Okay, so yeah, this is the last lecture of mine about the KPZ Universality class, especially exact solutions and related stuff. So let me recap what I explained yesterday. So we were focusing on the 1D KPZ class, and I was explaining yesterday solvable model, that is the PNG model, polynuclear growth model, and the main conclusion is this. So when we considered circular interfaces, curved interfaces in this model, it can be mapped in the space-time plot. It can be mapped to certain directed polymer problem, and this polymer problem is point to point. Okay, the two ends were fixed at some specific locations, and then we got GUE trace-width distribution. In contrast, if we considered flat interfaces, then the problem was actually line to point directed polymer problem. And then we considered the mirror image, and because of the different symmetry, we get GOE trace-width distribution for the flat case. Then in the end of yesterday's lecture, I showed you this table. So there are three main universality subclasses: circular, flat, stationary. And all these share the same set of the characteristic exponents, but the distribution is different. It is GUE trace-width for the circular case, GOE trace-width for the flat case, and the bike lanes for the stationary case. So it was the main result from the pioneer, from the celebrated work by Prefofo and Spon in the year 2000 for the PNG model. So in today's lecture, I'd like to start explaining how these look like in a few other models. And the first model I'd like to mention is the asymmetric simple exclusion process, or ASEP. And fortunately, Ivan already explained that in a way more general and sophisticated form. So I can go quickly here. So what I want to explain here is the most orthodox ASEP. So you have a lattice, and each side can be occupied at most one particle. And there is no color, anything. And each particle can hop to one of the neighboring sides with the rate q for the rightward hop and rate p for the leftward hop. And p and q are different, so that's why it's called asymmetric. And I said q is greater than p, so the particles tend to move toward right on average. And the only interaction between particles is volume exclusion. So if there is already a particle in your next side, this particle cannot hop. Each side can take only up to one particle. Okay, and then this model is famous as an integrable model for. So it's a famous integrable out of equilibrium model. So there are many exact solutions available about this model, and it is actually in the KPZ class. To see why it's in the KPZ class, we can map this particle model to the interface model, as Ivan explained this morning. So to map, I replace this occupied side with downward slope, and unoccupied side is upward slope. Then this configuration is mapped to this kind of interface profile. And suppose this particle hops to its right. Then it amounts to increase of this local height by a unit, right? So, and I recall you that particles tend to hop rightward on average. If a particle hops to right, the interface goes up. right? So you can see that this interface grows upward on average. So this is an interface growth model. There is a nonlinearity in the interaction. So and then on the basis of symmetries, at least, we expect it is in the KPZ class, and indeed it is. Then there are 3 universality subclasses, right? So how these 3 appear in this model? So it can appear depending on the initial condition you impose. For the circular case, the standard initial condition you consider is something called step initial condition. So the left half is fully occupied, and the right half is completely unoccupied. This corresponds to this kind of V-shape initial condition. And if you let this interface evolve, you will see some parabolic interface near the origin. So it's curved, and it corresponds to the circular case. To get flat case, you can consider this kind of alternating initial condition. And then this is mapped to this kind of zigzag interface profile. And it's on average flat. So it shows flat behavior. In the stationary case, the stationary measure of the ASEP is exactly known, and it is known to be a Bernoulli initial condition. So basically, you choose whether each site is occupied or unoccupied by some probability, let's say 50-50, and you just decide it independently for each site. That is a Bernoulli initial condition, and it's known to be the stationary state. And if you measure the interface height increment, you get the characteristic bike length distribution. So it is proven that all these initial conditions lead to the characteristic distributions I explained yesterday. So GUE trace-vidam, GOE trace-vidam, and the bike length distribution, even for the case of ASEP. I mean, totally ASEP is simple. So it has been solved in the early epoch of the exact solutions of the KPZ. But recently, even non-total ASEP has been solved for all these cases. OK. Now, I'd like to turn our attention to the KPZ equation itself. OK, so this is a 1D KPZ equation. And here I set coefficients like this. In fact, we can choose coefficients arbitrarily as you like. For any choice of coefficients, as long as these are not 0, you can just rescale x and t and h, and then you can get this KPZ equation. So we can set the coefficients like this without loss of generality. And here the noise term eta k kappa is chosen to be spatially correlated noise that I explained yesterday. So instead of the delta correlation in x, here I consider some function capital delta kappa, and this has some unimodal shape with width about kappa. So you have spatial correlation over length scale kappa, and in this way we can get rid of singularity at the at equal positions. So let us use this KPZ equation. And then yesterday I explained that the original KPZ equation is actually ill-defined. So the proper way to define it is to consider the stochastic heat equation with Ito product here. So let's start with this stochastic heat equation. And I'm going to rewrite it into another model, a few other models actually. And in order to do that, I like to use the standard calculus. So the Ito product is not convenient for that. So let me rewrite it to Stratonovich product. And then according to the conversion formula I explained yesterday, we have to have this kind of term. which goes to minus infinity if you take kappa 0 limit. Okay. Now, let's see it, this equation from a bit far away. And then it starts to look like Schrödinger equation. Yeah, I'm not sure if you agree, but it actually looks like Schrödinger equation in the sense that you have a first derivative of time in the left-hand side. And in the right-hand side, you have a kinetic energy like term. And you have potential term, right? Z is a wave function in this language. Okay, so this is Schrödinger equation. And then we can use knowledge from quantum mechanics that we can express the wave function by path integral, Feynman's path integral. There is a stochastic process version of the Feynman path integral, and it is called Feynman-Katz formula. And if we use that to this equation, we get this path integral formula for Z. And here, x of tau is path like this. This path should end at position x and t. This x and t are the argument of this Z. And about the initial, the lower end point of the path, it is distributed according to the initial condition of Z. Okay, now let's switch our mind from quantum mechanics to statistical mechanics. Then this starts to look like partition function, right? Z is sum of exponential something over all possible configurations of the path. So this is a partition function. If we see it in that way, these terms in the exponential are the energy of this path or the polymer. So let's call this path polymer. And this is a single valued function of tau. So actually this polymer is directed. It must be heading upward. And the energy of this polymer is consists of the this dx d tau squared, and it can be interpreted as elasticity, elastic energy. And the second term is, of course, random noise, right? It's noise term we had, and now it is a potential energy for the polymer. So the problem is now we have a directed polymer, and this polymer is placed in some random environment, and then you are asked to compute the partition function of this. And that's nothing but Z that we wanted to compute or evaluate. And then recall that our height function h is defined by log Z. If Z is a partition function, log Z is a free energy, right? Well, minus free energy. So what we wanted to see, characterize, is nothing but the fluctuations of the free energy of this directed polymer. Okay, now we want to characterize the distribution, fluctuation properties of the free energy or the partition function. One way to characterize the fluctuation properties is to evaluate the moment. For example, the nth order moment of Z is defined like this. You consider product of n Z at different positions, you take average, and this is the moment. Okay, so let's evaluate this. So we have expression for Z, right? So we just plug it into this definition of the moment, and we want to evaluate this average. To evaluate the average, we just multiply the probability density and integrate over eta here. Okay, so let me denote eta kappa at xn by eta n. And then we are going to evaluate something like, so we have a product of this z, right? So we have many product of this exponential. And eta is Gaussian distributed. So it's again exponential, right? Exponential minus eta squared.
Sorry, I'm a bit confused. How is this a function of x and t if x is being integrated over? And I guess what are the limits of tau integral?
So here, we don't change xt, and in the integral, tau is, I mean, sort of, how to say. So in this integrand, tau is just a given tau. You don't need to change tau inside.
But what are the limits of the integral over tau?
0 to t.
0 to t? Okay.
Oh yeah, tau is, yeah, tau goes from 0 to t. Here.
How is it a function of x?
X can be anything from minus infinity to infinity.
Oh, but it's pinned at
Yeah, the two endpoints of the polymer are basically pinned.
Okay.
Yes.
But I think part of the question is maybe in its eta k of x at time tau, and in the when you write eta k of x, it's x at time tau, no? In the
random potential.
In the random potential, so
yes.
x is a function taken at time. So in the part which is in the square, the red square, there is yes here
this one.
yes. So the x
Yes.
is taken at time tau there in the integral.
Oh yeah. So we consider a path x of tau, and for a given path x of tau, you evaluate this exponential. Yeah. So but of course there are many choices of the path x of tau.
Yes,
Yeah.
I think he's saying that the x there
Yeah.
is not the x on the left hand side of z.
Oh yeah, sorry. Indeed that's confusing. Yes, thank you very much. Yes. So these x are x of tau and not this x. Sorry. Yeah. Okay, so we want to evaluate this. And then probably you can see that we have to evaluate something like exponential to the power of eta n and averaged, right? I mean, this is what we see here. And as I said, to evaluate this average, we just multiply the probability density of eta, which is Gaussian. And of course, it is multivariate Gaussian distributions. So we have the covariance at the denominator here. And this is delta kappa. OK, so the equation looks a little complicated. But actually, it's nothing but the Gauss integral. So we can compute this integral without problem. And this is the result. I mean, this is nothing but the result of the Gauss integral. So we can compute this average. And the result is that the following. The moment it can be expressed as this kind of multiple path integrals of this form. And here, one interesting remark is that when I evaluated this Gauss integral, this sum runs over all n and m, including n equal m. And this result will be inserted here. And then actually the case with n equal m is cancelled thanks to this term, right? If you have n equal m, the argument of this capital delta is 0. So it exactly cancels with this term. So thanks to this extra term, now we don't have sum over n equal m. OK. So at this point, OK, now we get this. And this is a little bit complicated, but it's just a path integral. So we can use the Feynman-Katz formula in the inverted way. Now we go from the path integral to the Schrödinger-like equation, and we get this. So we get this kind of Schrödinger-like equation, and the Hamiltonian here looks like this. It just comes from this. Okay, and since we don't have summation over n equal m anymore, actually we can take the white noise limit without any problem. We take the kappa, the limit of the vanishing kappa, and this capital delta becomes a delta function. So this is the Hamiltonian we get. It consists of the kinetic energy term, and the potential consists of delta functions. And actually, it is a famous model known under the name of the Lieb-Liniger model. Lieb-Liniger model is famous as a quantum integrable model. And what we have done here is that I just converted. I started from the KPZ equation and converted by some multiple steps, and we ended up with this. So this is equivalent with the KPZ equation, or more precisely, the stochastic heat equation. And it is an integrable model. So you see that the KPZ equation has this kind of integrability. Yes?
But because you get to an integrable system, aren't you getting rid of the scaling of the KPZ to get to something else?
Something else.
I don't know, because I know for the integrable system you have the generalized hydrodynamics, we talked about this, and so this predicts other scalings than the one that you get from KPZ. But Lieb-Liniger is very well described by this theory, so isn't that a problem?
Okay. Application of generalized hydrodynamics is a bit tricky because it is very nice framework to describe integrable systems with ballistic transport. For ballistic transport, it can evaluate the Drude weight, which characterizes the ballistic transport. But the case of the KPZ is not ballistic, but it's super diffusive. So it's a bit tricky. But
getting to the same equation because you have the same Hamiltonian as Lieb-Liniger, or is it maybe because you don't have an I before your time derivative, that it's a different system? I don't know. That's what I'm asking. Because if you're showing me this, you're showing me Lieb-Liniger, and I know that this is described by this framework.
Okay. I don't know if that kind of approach is possible. But I'm going to tell that actually this Lieb-Liniger model has a strange property as thermodynamic model. So one remark I can tell to everybody is that this, in the literature, usually the sign of the potential term is plus. And that is called the repulsive Lieb-Liniger model. That is the standard model considered in the literature. However, the one equivalent with the KPZ equation has negative sign here, so it is called the attractive Lieb-Liniger model. Okay. Okay, so so this is basically what I showed, and then yes.
Maybe can you comment on the fact that it's attractive, because so this morning Ivan explained us that KPZ is related to repulsive Brownian motion. So these lines of Brownian repelling Brownian motion, and now I see Laplacian and then something attractive, and I'm getting confused.
I think these two objects appear in a rather different context. Repulsive Brownian motion appear as a model of to realize or interpret the Dyson's Brownian motion. You have many eigenvalues, and eigenvalues do not cross. They are ordered, and they do not cross. And it can be expressed as a repulsive Brownian motion. Here, I don't deal with the Dyson's Brownian motion. I just converted the KPZ equation to something else, and then we get this. So x here has nothing to do with the large eigenvalues of the Dyson-Brownian motion. So the variables are actually very different between the two cases. So yeah, here we have attractive interaction. Okay, and then I was telling yesterday that the initial condition is important. So let's consider first the circular case. To consider the circular case, for the KPZ equation, we usually consider this kind of wedge initial condition. So this V-shaped initial condition, and then the interface will grow from this V-shaped initial condition. So the top part is parabolic, and it's curved. So it's expected to be the circular case. And then Z is exponential h. So you put this to the power of this exponential, and then you can take kappa infinity limit. This is a narrow wedge limit, and this Z goes to the delta function. That's great because in terms of the polymer, it means that we can fix the lower endpoint at the origin. So actually, even in this KPZ equation case, it's mapped to the directed polymer problem with point-to-point configurations. Yes?
Is this the same kappa as we have for the white noise revenue?
Oh, sorry, I abused the variable. Yeah, sorry. It's another kappa.
The two limits independently, right?
These two kappas have really nothing to do.
Okay.
Yeah.
Sorry, can you please comment when the statistics, when you write down bosons,
Yeah.
and where exactly we see the statistics is boson, is bosonic,
Oh.
where it happens?
Well, so our x, we have many x. These x came from replicas. So we considered nth order moment.
So we can permit this, and the wave function doesn't change. So we
Right. You can see that first different x can overlap, and even if you exchange labels, it doesn't change the wave function. So it has the symmetry of the boson particles. Okay. Okay. So yeah, I said that the circular case is a point-to-point problem, and then the question is how to solve it. So we have the Lieb-Liniger model with the attractive potential. Then all we need is so let's focus on the fluctuation properties at x equals 0. Okay. So all x here, where? Yeah, all x here are set to be 0 now. At time t. Yeah, so we want to solve this, just the nth moment of z at x equals 0. According to our formalism, it can be expressed as by this kind of expression. So we start from the point initial condition, right? All bosons were at x equals 0 initially. And then it evolves by this Hamiltonian. And at time t, again, we want to see what matters is the case where all bosons aggregate at x equals 0. Okay, and then it can be expressed by this kind of expansion. We just expanded over all eigenstates. Okay, and then we can actually solve this by using the integrability of this model. So there is a method called Bede-Ansatz, and here we assume that the wave function can be expressed as a superposition of plane wave-like solutions, like this. But here you have a permutation of the label for particles. So this is an assumption we can set to try this beta-ansatz solution. And you have some coefficient AP here. And the form of this AP can be determined by plugging this plane wave solution to the original Schrödinger equation with this Hamiltonian. So if you put this form to the Schrödinger equation, and in order to satisfy the Schrödinger equation, you can actually get this form for AP. And then, so we kind of get the form of the wave function. So we can actually evaluate this sum over all eigenstates. I mean, each plane wave-like solution becomes an eigenstate of this Hamiltonian. So we can sum up all over all eigenstates. So each eigenstate is labeled by a choice of lambda, which is called quasi-momentum. But actually, this quasi-momentum is not a real number, but it can also be some complex numbers. But not all complex numbers are admitted. There is actually a specific form that is allowed to take. I mean, this lambda must be expressed in this kind of form. So real part can be any real number. Kj can be anything. But there is a strong constraint on the imaginary part. It must be expressed by this kind of discrete form. And so this condition can be found in order for the wave function to be well defined. I mean, if you integrate the squared modulus of the wave function over all space, it must not diverge, right? If you impose this condition, you actually get this. Only when lambda satisfies this condition, the wave function does not diverge. Okay, and it can be expressed in a graphical way like this. So what we do here is that suppose we have n particles, let's say 9 particles. First we group 9 particles to some groups. I mean some groups called strings. Let's say we group it to 3 strings. The first string has 3 particles. The second string has 2 particles, and the third string has 4 particles. It is just an example. You can distribute anyway as you like. And then this condition says that the first 3 particles in the first string must be distributed like this. They have to have the same real number, and the same real part, and the imaginary part must be distributed like this. And spacing is always 1. So if you have, so the imaginary part is minus I, 0, and plus I. If you have only 2 particles, it must be minus 1/2 I and plus 1/2 I, and so on. So given the number of particles, I mean total number of particles, you can consider there are many possibilities to distribute n particles to many strings, right? So you consider all possibilities, you sum up over all possible configurations, and you can evaluate this sum. Okay, and we need energy for each eigenstate. And it is straightforward to compute energy by using this plane wave like solution and the Hamiltonian. So energy is just lambda squared, sum of lambda squared because of the kinetic energy term. And lambda is given by this form, so it looks like this. Okay, and now we notice, I mean, this E is the energy. So if this model is a thermodynamically sound system, we expect extensivity to this energy. However, in the right-hand side, we have something like m cubed. M is the number of the particle in a given string. So actually, this energy grows like n cubed, so it is not extensive. So it is a very strange model as from the thermodynamic viewpoint. And that's why it is not usually considered in the literature of quantum integrable systems. But this is what we need to deal with in the KPZ case. Okay, so this is a problematic term. But actually, there is a nice formula telling that exponential n cubed is something like this. It can be expressed as the integral of Airy function. So by using this, I mean, you have something like m cubed as the energy, and it will go to the power of this exponential. So actually, it has a form similar to the left-hand side here. You can relate it in terms of the Airy function. And then, actually, this is the source. This becomes the source to the Airy kernel, which I used to define the, to express the Tracy-Widom distribution. So what people did is that using this relationship to Lieb-Liniger model, these people showed that indeed the GUE Tracy-Widom distribution can be obtained for the KPZ equation with the wedge initial condition. So this is the characteristic distribution for the circular subclass. So that's the story about the circular case KPZ equation. But as you can see, this approach is not rigorous. First, we exchange infinite sum and integral many times. Secondly, it is known, we evaluated the momentum, right? Statistical moment. It is known that even if we get moment up to infinite order, it is known that we cannot obtain the corresponding distribution uniquely. So we cannot rigorously say that the Tracy-Widom distribution is obtained by this approach. It is non-rigorous, highly non-rigorous approach, but the result seems to be correct. And actually, there are totally different ways which are mathematically rigorous to start from the nano-wedge initial condition of the KPZ equation. And indeed, the GUE Tracy-Widom distribution was also obtained with mathematical rigor by completely different approaches. So with this, we can also believe this result. But what is nice here is that we have some physical picture. You see, it's related to quantum integrable model. And because of this Bethe-Ansatz calculation, we indeed see some piece of Tracy-Widom distribution, Airy function. So this is what I wanted to tell here. Okay, so for the circular case, it is a point-to-point problem, and we get GUE Tracy-Widom. Now, what about the flat case? Flat case corresponds to the flat initial condition. And so Z is also constant. It's flat. Then remember that the lower end of the polymer is distributed by this Z at time 0. It means that this lower end is distributed uniformly along this line. So again, the flat case corresponds to the line 2-point problem of the directed polymer. Okay, and I don't explain detail, but again, by using the Bethe-Ansatz approach, this paper by Pierre Ledussard and Calabrese showed the GOE trace unit distribution for this case. Okay, so yeah, this is about the KPZ equation. If you have questions, maybe you can ask. Good. Okay, and here let me just remark how to compare with these characteristic distributions if you deal with, let's say, experimental data or simulation data. All data are obtained in the physical unit, like space and time, real time, and so on. But of course, these characteristic distributions are expressed in terms of some rescaled quantity. So we need to know how to rescale. And well, for the sake of time, I just explain the result. So we know that in the KPZ, 1D KPZ class, height h grows like this. So the leading term is proportional to time, and it's deterministic. There is no fluctuation here, and we can define the asymptotic growth speed v infinity. Fluctuations come in the subleading term, which grow like t to the 1/3. This 1/3 is the exponent beta. And we can define some amplitude coefficient gamma here. And we know that the spatial coordinate x must be rescaled by the correlation length xi. And okay. And actually there is a formula for this correlation length xi, but this xi grows with the power of t to the 2/3 in the 1D KPZ class. Okay, so we have two scaling parameters which can be determined by plotting h against time. And another thing we need to obtain is some parameter that scales the correlation length, that is used to rescale the correlation length or space. And in order to do that, it's convenient to use this quantity. It's called the height difference correlation function. You just take the difference of the height at positions separated by distance L at equal time. So you take difference, you take squared, and take average. And actually, it is nothing but the mean square displacement if you regard the interface profile as a trajectory of some Brownian right motion. And I said that the stationary state of the KPZ equation is equivalent to the Brownian motion. So as a result, this mean square displacement should grow proportionally with L. And we can define the proportionality constant A here. And then we also need to determine lambda, which is the coefficient for the KPZ nonlinear term. And actually, it's known to be obtained by this. So here, we measure the asymptotic growth speed v infinity as a function of the slope of the interface. So suppose you start from some slope, some initial condition with finite slope. You let it evolve, and you get the growth speed as a function of u, tilt u. And then you evaluate this, and you actually get KPZ coefficient lambda. And for some simple case, I mean, for the case of isotropic growth, so if the interface wants to grow in all directions at the same speed, then actually we can derive that v infinity should look like this as a function of u. And from this, we can show, I mean, if we put it into this equation, we get lambda equal V infinity. So in the case of the isotropic growth, which is not unusual in experimental systems, we don't need to evaluate this equation, but you just evaluate this V infinity, which is the asymptotic growth speed, and then you get lambda. Then it's known that this gamma here is just a square lambda divided by 2. So all you need is actually you obtain A from this height difference correlation function. And in the case of isotropic growth, you evaluate the asymptotic speed, and then you get gamma here. So you can rescale your height fluctuations, and then you can compare this chi with chi for the Tracy-Widom distribution or bike-length distribution. So this is the practical method to test characteristic distributions with your simulation or experimental data. OK. Now, so far, we only dealt with the one-point fluctuation property. The natural question is if there's anything we can say about the multi-point correlation properties. The answer is yes, especially for equal time multi-point correlations. There is a lot of things. There are a lot of things known in the literature. So actually, the limiting processes are characterized for all the 3 universality subclasses. Limiting processes mean, so so this is a profile of the interface for each case. I mean, for one given case, let's say. Horizontal axis is x, and vertical axis is h. And of course, if we want to characterize asymptotic properties, I mean the scaling limit, we have to scale x by, we have to rescale x by the correlation length. So you divide x by xi, and fluctuations of h should be divided by t to the 1/3. And then your interface looks statistically stationary in this representation. And in the time infinite limit, this trajectory can be expressed as a kind of stochastic process if you regard the horizontal axis as time. So this is the limiting process, which characterizes the equal time multi-point spatial correlation properties. And that limiting process is characterized exactly for each of the universality subclasses. And it's called Airy-2 process for the circular case, Airy-1 for the flat case, and for the stationary, it is just a Brownian motion. OK, so by using this Airy process, the rescaled height that I defined in the previous slide, this one, chi, as a function of x over xi, this should converge to this kind of object. So for the circular case, it converges to Airy-2 process minus parabola, which reflects the curved structure of the interface. For the flat case, it converges to the Airy-1 process. Yes?
In the former lecture, you discussed the fact that the Brownian motion was a solution of the Fokker-Planck equation.
Yes.
So that's not the only one. So why in other cases we find something else?
The point is that to get Airy-2 Airy-1 processes, we need to rescale this. So actually, I had to write, instead of x, it must be x divided by xi. And h, instead of h, it must be h divided by t to the 1/3. If we take that scaling limit, then the profile can be something else. I mean, if I don't rescale and look at the bare h as a function of bare x, then in all cases, it goes to the Brownian motion. And that's what the Fokker-Planck equation tells. But if I take a different scaling limit, I mean, if I rescale x by t to the 2/3, which is the correlation length, and if I rescale h by t to the 1/3, then the profile may look something different. And that is the Airy process. OK, so this Airy process contains the information, I mean, full information of the spatial correlation properties. So we want to know what kind of object it is. Yeah, so there are determinant formulae for Airy 1 and Airy 2 processes. So if you are interested, you can see the explicit mathematical formulae. But actually, there is a nice representation for the Airy 2 process based on the random matrix theory. So it is known that the Airy 2 process is nothing but the top eigenvalue of Dyson's Brownian motion, which you already heard several times in this school, right? So as Ivan explained already this morning, in Dyson's Brownian motion, especially for GOE matrices, we consider a matrix A, which is a function of time. So each component of the matrix has time variable, and it does Brownian motion. So of course, off-diagonal elements have real part and imaginary part, and both of them do independent Brownian motion. And they start from origin at time 0, and then the eigenvalues scale like square root of t. And if you rescale this lambda I mean i's eigenvalue by square root of t, then you actually get some stationary stochastic processes. And if you look at the top eigenvalue, this is nothing but the Airy 2 process. So yeah, I recall you that if you look at the 1-point property for the circular case, it was the GUE trace-random distribution. It is a distribution of the top eigenvalue of GUE random matrices. Now you look at multiple x at equal time, then this result says that it is nothing but the top eigenvalue of GUE random matrices, again, at multiple times in this frame, in this representation. And if you find this rescaling a bit annoying, you can actually consider Ornstein-Uhlenbeck process instead of the simple Brownian motion. So if matrix A is evolved by this kind of time evolution equation, so now you have a restitution force because of the parabolic potential. And then you can get stationary process in the eigenvalues, and you can. This is also the same Dyson's Brownian motion without this square root of t dependence. Anyway, so from this Ornstein-Uhlenbeck process, you obtain lambda max, and you rescale in this way, and you can get Airy 2 process in the large matrix limit. Okay, so this is the Airy 2 process. Then what is Airy 1 process for the flat case? For the flat case, if you look at 1-point fluctuations, it was GOE trace-random distribution. So the top eigenvalue of GOE random matrices. Then if you remember the result for the circular interface, the multi-point correlations were GUE's Dyson's Brownian motion. So a natural expectation would be that for the flat case, probably it is the Dyson's Brownian motion for GOE random matrices. But that is not the case. Somehow, so Airy 2 is identical to the top eigenvalue of GUE Dyson's Brownian motion, but Airy 1 turned out to be not the top eigenvalue of GOE Dyson's Brownian motion. If you plot, I mean, this is a plot taken from this paper, and if you plot the covariance of the two processes, then it is clearly different in the case of the ARE1 and GOE Dyson's Brownian motion. So unfortunately, to evaluate ARE1 process, we really need to evaluate the determinantal formula obtained for the ARE1 process, and we cannot approximate it by Dyson's Brownian motion. And the way the covariance decays is actually quite different. For the circular case, I mean for the ARE2 process, the covariance, covariance defined like this decays by a power law, u to the minus 2. But for the ARE1 process, the covariance decays super exponentially fast, exponential minus u cubed. It is quite surprising, at least to me. I mean, your spatial correlation of your interfaces decays in a qualitatively different way between the circular and flat interfaces. But this is a result from the exact studies on the KPZ class. Okay, so these are some main outcomes of some of the main outcomes of the exact studies on the 1D KPZ class that I wanted to tell in this school. So if you have questions, I can take. Yes.
So for both of these processes, the ARE1 and the GOE Dyson Brownian motion, the 1 point marginal is correct, right? It's the GOE Tracy Williams,
Yes.
but the problem is just with the correlations.
Yes. Is there anything else?
You say it was
Yeah,
not clear,
yes.
but the two behavior are very different at long time. Then one keeps track of the fact that one decays as a power law, and there is a long-term memory, and not in the other case. You have some intuition on that. I guess the same.
Okay, I don't have it. Yeah, well, you said memory. I mean, memory, the term memory is correct for the ARE process as a stochastic process, but for the interface, it is about the spatial correlation property. It's not time, so.
That's not in time. That's spatial still.
Yeah, I mean, for the interface, it is space. Tau is space.
But, I guess similar question. It's assuming like so this distribution for the 2-point function is valid at all times, and is drastically different for different initial conditions. So this is surprising, or should we not be surprised?
Well, from the okay, I cannot tell how surprising it is from the mathematical viewpoint, but at least from the physical viewpoint, I was surprised by this qualitative difference.
And do you have some intuition for what makes it remember?
Myself, I don't have, but I'm sure mathematicians or mathematical physicists working on this subject have some. I mean, there are some diagrams we can draw in this context, and I think there is a way to discuss on the basis of that diagram, but I'm afraid I cannot explain that. Okay, then let me switch here, and I'd like to explain to what extent this kind of exact results can be tested with real experiment. So there are many exact solutions to many kinds of models in the 1D KPZ class. But to my knowledge, all of these benefit from the integrability of the models. But there are models or systems that are not integrable in the 1D KPZ class. So to me, it is not trivial if properties obtained for integrable models are kept exactly the same even in non-integrable models. So, and integrability is a special kind of property. So, and usually I don't expect integrability holds in just a randomly chosen experimental system. So that was important motivation, at least for me, when I did experiments on the 1D KPZ class. So it is to test. One motivation to do experiments here is to test to what extent properties obtained for integrable models are kept valid in non-integrable systems, especially experimental systems. Okay, and the system I used is convection of liquid crystal. So basically, I have two parallel electrodes, and liquid crystal is sandwiched between the two electrodes. And we can apply an electric field perpendicularly to the surfaces, and this electric field is known to drive convection in liquid crystal. And if the applied voltage is high enough, the convection becomes turbulent. And there are two turbulent states called DSM1 and DSM2. The main difference is that DSM2 consists of many topological defects in the nematic ordering. It's called discriminations. While in the DSM1 state, there is basically no such topological defects. And let me show a video. So here, the system is in the DSM1 state. And DSM1 state is actually metastable under high enough applied voltage. So if you wait a little bit, you see spontaneous nucleations of the other turbulent state, which is DSM2 state. And it is followed by growth of the cluster, because DSM2 is a stable state. So you see many growing clusters in my experimental system. We do see the boundary or interface, which is fluctuating. So if KPZ class is robust enough, we should see KPZ behavior here. Okay. Yes, but actually it's not straightforward to test fluctuation properties of the KPZ class here. Firstly, because we have too many clusters, and these clusters merge at some time. So it's hard to extract statistical properties from this kind of thing. Then what I did is that I wanted to control the nucleation. So by using a lower applied voltage, we can actually reduce the spontaneous nucleation rate. So basically, now spontaneous nucleation is a very rare event, so it doesn't happen. But by irradiating a laser, by using laser, we can actually induce nucleation by using some process called photoisomerization. So usually my liquid crystal molecule, it has a straight shape like this, but by irradiating a UV light, the molecular shape changes to this kind of V shape. And so the nematic ordering is reduced, and it facilitates generation of topological defects. In this way, the growing turbulence is generated. So here, I will send a laser pulse to the center of the camera field. And this indeed generated a single growing cluster, circular cluster. This is way easy to analyze. We have only isolated cluster at the center of the camera field. And we can repeat it many times. I just turn off the applied voltage. Everything is reset. I turn it on again. I shoot a laser. I record it. It can be repeated automatically. And after one day, I get 1,000 clusters. OK, so that's what I did. And another advantage of using light is that we can change the initial condition. Here, I sent a laser pulse at the center of the field. But I can also shoot it along a line here. Then it makes a flat interface. So by using the same experimental system, we can compare circular and flat interfaces. All right. So I need to define the height. For the flat case, it is defined as in the usual way. For the circular case, we can actually use the local radius as height, and x is defined along the circumference. Okay, and then we can evaluate the standard deviation of h, and this is the result. So the standard deviation is plotted as a function of time in the log-log chart, and in both cases, circular and flat cases, we see that the standard deviation grows like t to the 1/3. And this 1/3 is a KPZ exponent beta. Okay, so indeed our height grows according to this equation. And then there is a way to evaluate gamma, as I explained briefly in some slide back. And so we can obtain chi here, and this is the distribution. Here actually we have to deal with finite time correlation. Finite time correction. And what I'm showing here is the result after the finite time effect is subtracted.
And what is exactly this time effect? You
Yes.
should wait for quite long time in order to measure? Or?
Yeah, I mean, in any case, the KPZ behavior is something asymptotic. So we have to wait long time. It's hard to tell how long time is necessary a priori. My big fortune is that somehow this system behaves like in the asymptotic limit from the beginning of the video. So I don't know why actually. Then the finite time effect I told is actually this. So this is an equation I already described, but this is not the end of the equation. We have subleading term, more subleading terms. The next order is t to the 0. And what I plotted here is actually a rescaled quantity defined by this. So if we don't have subleading term, then it is nothing but chi here. But because of this subleading term, it gives chi plus something t to the minus 1/3. So if I just plot the histogram of this h tilde, I see deviation from the trace-Widom distribution in the order of t to the minus 1/3. But that deviation was indeed confirmed to decay by t to the minus 1/3. So I evaluated the coefficient in front of this term, and I subtracted it. This is what you see here. Okay, so circular and flat interfaces indeed show different distributions. Circular case is a GUE trace-Widom distribution. Flat cases, it is GOE trace-Widom distribution. I tell you one story. When I did experiments, I didn't believe these exact results, because circular interfaces become flatter and flatter as time elapses. It looks really like flat interfaces if your time is large enough. So from my physical intuition at that time, it must not show different distributions. So I wanted to disprove what the mathematicians said. Then I found this data. Yeah, I was convinced. So I failed to disprove such results. So yeah, I was surprised. I mean, even if the interface shape looks quite similar for large enough time, the distributions remain different forever. But that's a fact. I mean, this is what I was taught by my experimental system. Okay, so this is the result. About the spatial correlation, well, we have data, so we can evaluate the equal time 2-point correlation. And I rescale it in the appropriate way, and this is the result. The colored data are experimental data, and actually there is a black dotted line here and black dashed line here, and these are the predictions from the ARE 2 process and ARE 1 process. They are in very good agreement. And there's no arbitrary fitting parameter. So yes, and I said that it is surprising that ARE 2 and ARE 1 have qualitatively different decay. But that is also confirmed with this experimental data. Okay, and what about the time correlation? So here, the quantity to consider is equal position and 2-time correlation function. And at that time, when I did the experiments, it was an object that is hard to deal with from the theoretical or mathematical approaches. So there was no solution. So, but I have the experimental data, so I evaluated, and this is the result. So here I plotted the 2-time correlation functions as a function of T2 over T1. And I changed T1, so how to say, for several T1, I plotted this against T2 over T1. And for the flat case, the correlation function decays as expected. For the circular case, it does decay, but somehow it decays very slowly, right? 0 is here. And this becomes clearer if we plot the same quantity in a different way. So here, y-axis is a rescaled 2-time correlation function. And the x-axis is delta to the minus 2/3. And delta is the rescaled time increment, T2 minus T1 divided by T1. So, so infinite time increment corresponds to going leftward in this plot. And if you see data for the flat interfaces, it seems to go straightly toward 0. But for the circular case, the data seem to go somewhere which is clearly different from 0. So it means that even if infinite time has passed, there is some strictly positive correlation remaining in the circular case. I found it weird, but actually thanks to great theoreticians, we work together, and they basically get theoretically, I would say, approximate solution to this 2-point quantity. And they actually gave a very clear physical picture to explain this difference. So I recall you that the KPZ equation can be mapped to the directed polymer problem. And now 2-time problem is expressed as 2-polymer problem. The first polymer is spanning from time 0 to time t1. The other polymer is spanning from time 0 to time t2. Then the correlation between the two heights is the correlation between the two free energies of the two polymers, right? And these two polymers are placed in the same random potential. Now, for the flat case, it is a right 2-point problem. So if the if time t2 is sent to infinity, then two polymers basically take completely different paths. They can arrive at anywhere at time t equals 0, right? So it can take completely different paths. But for the circular case, two polymers need to arrive at the same point at time 0. So even if you send the upper end of this yellow polymer to infinitely far, this yellow polymer has to go somewhere very close to the red polymer near time 0. So they cannot avoid some overlap. And that's why we have correlation between the two free energies. And that's what we see here in the experimental data. So this is a physical intuition why the two cases have very different correlation properties in the time correlation properties. And then, so it was the year 2017, and in this year and around this year, there were a lot of development on the mathematical side, and mathematicians developed a way to deal with this kind of two-time and multi-time properties. And in the end, this result was proven mathematically. So some theorem was made on two-time correlation functions. And again, of course, this theorem was consistent with experimental results. So what I like about the KPZ class and what I think is special is that KPZ class, 1D KPZ class, spans not only theoretical physics, but experimental physics and mathematics. So some result from experiment may even affect pure mathematics. And the theorem can be, of course, it's not contribution from us, but I mean, these kind of things are related tightly, and we can compare things directly. That's something I find very nice about KPZ. Okay, and okay, this is to tell that experimentally we can now generate any kind of initial conditions, even KPZ initial condition. I don't know what kind of distribution it gives. But by using this technique, we can also generate stationary interface. I mean, in order to get stationary interface, we have to wait infinitely long time, right? But we cannot wait infinitely long time. So actually, there was no direct test of the predictions for the stationary state. But by this technique, we can generate a Brownian initial condition. So we can test predictions for the stationary state. And indeed, we found the bike length distribution, as well as for the stationary case, actually the two-point correlation function for different positions and different times was also evaluated. I mean, exact solution was obtained. And this was also confirmed by experimental data. Okay, and one natural question was, I mean, I showed that different initial conditions may lead to different statistical properties. So what happens for general initial conditions, arbitrary initial conditions? There is a nice formula to deal with general initial conditions, and that is called the variational formula. And recall that for the KPZ equation, it is mapped to the directed polymer problem. And the circular case was the directed polymer problem with point-to-point configurations. So the initial condition was the delta function. It means that the solution for the circular case can be regarded as a kind of green function, right? It is a solution to this delta initial data. So by using this fact, actually we can show that Z from arbitrary initial conditions can be obtained in this kind of form. I mean, I recall you that D is a solution to the stochastic heat equation, which is a linear equation. So we can use the technique of the green function. The result for Z of xt can be expressed by using the green function in this way. But of course, here we neglect the fact that it has a disordered random potential in it. And this random potential is not correctly treated when I describe this kind of thing. So actually, this equality is valid only for the one-point quantity, like the distribution function. And by using the rescaled quantities, it can be expressed as a SUP problem, variational problem. So you have initial condition H0 plus solution to for the circular case. And you take SUP for this y, and then you get the one-point quantity for x and t. And actually, there is a nice graphical representation to this variational formula, for this variational formula, which I call KPZ Huygens principle. So suppose you have general data, general initial condition, h of x and 0. Then we regard this line as a series of point sources for circular interfaces. And suppose from each point source you have circular interface, then this formula tells that we only need to take the envelope of these circular interfaces. Then this envelope is nothing but this soup. And according to this formula, it gives you the correct one-point quantity of the height from this kind of general initial condition. So it's really like Huygens principle of optics, but with some fluctuations in circular, interface systems. Okay, and the validity of this variational formula was also confirmed experimentally. And I want to remark that this morning, Ivan talked about the object called the directed polymer. Directed landscape. Actually, the directed landscape or the airy seat are kind of extensions of this concept. So the variational formula here can tell us only the one-point quantity. But by using the directed landscape Ivan talked about this morning, we can actually get full statistical properties from general initial conditions. So there are a lot of progress from the mathematical side to deal with such general cases. How to say? Now we can, how to say? I wouldn't say all, but we can really deal with many kind of situations by using such mathematical objects. And we see relation to many concepts like random matrix theory and airy processes and so on.
Sorry.
Yes.
So this is the same formula for crystal growth, the Wolf construction, or it's different?
Crystal growth.
Yeah. So you start from some core, and then you.
Oh yeah, polynuclear growth model.
Is it the same?
Same in what sense? So the model is different, right? I mean, polynuclear growth model that I talked about yesterday is a specific model in the KPZ class, and that model is not directly used to construct this kind of formula.
Is there it's called Wolf construction.
Wolf construction.
It's also a variational principle that you can determine given the symmetry of the crystal, and then you can determine the shape of the crystal.
Okay, crystal. I mean real crystals. Yeah. Okay. So I don't know that. So maybe you can tell me later. But my impression is that if it is about real crystals, probably it is something different from this. Yes.
It's the anisotropic version of this construction.
Okay, thank you.
Where the velocity depends on that.
Okay, thank you very much. Okay, so probably I have only a few minutes left. So I don't think I can fully explain this last chapter, which was kind of expected. But I just want to give a few words that I wanted to tell in this chapter. So the world of the KPZ class is expanding. I mean, it was first established by Meheran and Parisi-Zhang as a class for interfaces, but not only for interfaces. In their paper, already relation to the Vargas equation is discussed, relation to directed polymer is discussed. So from the beginning, KPZ is known to describe many kinds of problems. But that scope is expanding very fast, in a very surprising manner, especially in recent years. Now, some nonlinear fluctuating hydrodynamics can show properties of the KPZ class. And to me, the most surprising correction, very recent correction, was a possible relation to spin chains. And actually, what the model discussed here is the Heisenberg model, which you may learn in a class of statistical mechanics. So it's a model for spins, and it's an integrable model. So it has some special transport properties. And in the case of the isotropic interaction, I mean, if this coefficient is 1, which is called XXX chains, then it's known to show super diffusive transport. So the correlation grows like t to the 2/3, and this is identical to the exponent of the KPZ class. But of course, this 2/3 is just a simple rational number, so we shouldn't say KPZ only from this. A real surprise is that the 2-point function of the spin at equilibrium state turn out to be very close, at least, to the KPZ's 2-point function. So it seems to have something to do with the KPZ class. And actually, I and collaborators did some simulations on these spin chains. It turned out to show not only the 2-point function at different positions and different times, but it also shows the some part of the bike length distribution. It also shows the equal time 2-position correlation functions, and it also shows that equal position 2-time correlation function. So there are many quantities that appear as is in the spin chain model. So there must be some, in my opinion, there must be some relation between the KPZ class and this kind of spin chains, equilibrium state. But actually, the correspondence seems to hold only in the 2-point quantities. Actually, the symmetry is already different. The KPZ interfaces are about interfaces growing upward or downward. I mean, it's growing somewhere, right? So there's no up-down symmetry for the height. But for the spins, it's symmetric. Up spin and down spin are symmetric. And if you look at spin current, it can positive current and negative current are symmetric. So the symmetry is completely different. And for the stationary state, if you look at the height distribution, it is a bike length distribution. And it has an asymmetric shape. But for the spin, corresponding quantity is integrated current of the spin. But if people take a histogram for this quantity, it is a completely symmetric distribution, as it should be. So the 1-point distribution is totally different. And higher order quantities are also different. But somehow, 2-point quantities are exactly the same, as far as I can analyze numerical data. So somehow, the spin chains have overlap with the KPZ class in this kind of partial manner. And no one understands how and why this happens. So it is in a very interesting situation or mysterious situation that I definitely like to understand. But it seems to be not an easy thing to do. So I just want to show it as an outstanding, probably open problem in recent progress of the KPZ class. Then I'd like to end my lecture by going back to this history, which I showed in the beginning. So left half is the history of the equilibrium critical phenomenon. Right half is the history of the KPZ class. And if we compare the two histories, I think now we have exact solutions, many exact solutions. We have experiments. we have a more kind of general understanding of the mathematical structure. But it can be questionable. But I would say that our situation is probably comparable to here. We have experiments, solutions, and so on. But probably we need something new, like renormalization group or I don't know, conformal field theory, to how to say, to cook up all these exact developments found by mathematicians and mathematical physicists in some kind of framework to tell us the real physics picture. So I hope this kind of how to say fundamental progress will be made further in this history. I mean, in this ongoing history of the KPZ class. And from another viewpoint, our speaker of this morning wrote some review paper nearly 10 years ago. It's a monograph. And actually, he compared the KPZ class with the central limit theorem. Central limit theorem is, of course, about some of independent random numbers, right? Or random numbers can be weakly correlated, right, in the central limit theorem. Somehow, the KPZ class or the Tracy-Widom distribution especially seem to appear in many apparently different problems. But in all these cases, random numbers are strongly correlated. So somehow, Tracy-Widom distribution tends to appear in such strongly correlated problems. And this seems to have some universality for this kind of problem, I mean statistical problem. And he noted, he actually described many open problems. It's really interesting to read. And and I forgot if I think I emphasized, but it went somewhere. So he said it took 200 years, some 100 years to construct the central limit theorem. 200 years from the discovery of the Gaussian distribution to the first proof of the central limit theorem. So probably we are, how to say, kind of seeing some pieces of possible putable central limit theorem for strongly correlated problems. I hope it doesn't take 200 years, but I hope we can get something as meaningful and as fruitful as central limit theorem. With this, I'd like to end my lecture, and I'd like to thank to everybody. Thank you very much.
So maybe we take one question because we're limited and there is something else after. But okay.
Yeah. What happens to the universality subclasses if you put it on, if you change the geometry of space? So you put it on like a sphere or cylinder.
Oh, you mean higher dimensional cases? So the exact solutions were obtained for the one-dimensional KPZ class. So in terms of the interfaces, it is about line interface growing in two-dimensional space. But of course, we can consider higher dimensional versions of that.
No, so the dimension's the same, but maybe you have like a two-dimensional, like you take your experiment, for example, but what if the sample was curved?
Oh, I see. Well, from the experimentalist viewpoint, I didn't do such experiments. So I have no answer to give. But I think the point is what kind of symmetry that geometry has. I would say if it is just a sphere, and if we have an interface growing in on that sphere, I think it should be similar to the circular case. So I don't expect the change of the distribution property. But you can actually play with many kind of metrics in this case, and there are people who consider random metrics, and so the randomness is in the metrics, and the growth process itself is deterministic. Then, because of the random metrics, the interface may look random, And indeed, in that case too, the people found numerically the Tracy-Widom distribution. So there is some universality even kept in this kind of setting.
I think we can continue the discussion. That's perfect. And thank you again.
Thank you very much.